Without further ado, let's look at what Apache Cassandra has got to offer. NoSQL is actually more knowing about your queries. Applications, and obviously there's a lot of good intro to NoSQL that has happened. If you have to take one slide away from this whole talk, my talk, it would be you would have to know your queries up front. You'd have to know them very well. At least 80% of your application uses mostly the same queries. And so you're paying cost for being the versatile. SQL is great. It is very versatile. It gives you a lot of flexibility to change your queries on the fly, in the runtime, in real time, after you built your application. But turns out most applications, when they scale, end up having to apparently using only a very small set of their real functionality more frequently, the 80-20 rule. And as a result, what your application is really depends on how it performs, really depends on a small set of queries. So imagine you had to redesign your application or redesign your schema such that those queries are answered really well. And that's the crux of the problem that NoSQL is trying to help with. And I'm kind of imagining most applications will end up fitting into that space. There are some applications which would not, and those are not the ones we'll talk about. So with that, I'll just give a brief on what the topics are going to be. Just talking points, so feel free to stop and ask questions as we go. It's going to be asynchronous. Run through some use cases on why Cassandra and how Cassandra should be the reason for your NoSQL adventures. And we'll talk a little about the use cases. Obviously, pepper it with lots of different use cases. There are more use cases in my mind, so if you have any more questions, we'll probably answer it with a use case. So try and see if it fits your kind of use case. And there is, up front, there is a lot of obvious discussions when Cassandra comes up, eventual consistency pops up. So we'll talk about that. We'll see why and how, and what use cases fit and what use cases do not. So, and obviously, the number one reason for adopting Cassandra will be the community and the vibrant community around that code. The code also speaks for itself, very brand new code, so you look at that, and there's a journey of tools that are being built as in the last few months as well. It's a fast-moving project, so the community around Cassandra is definitely rich, and that's kind of one of the reasons I got excited about Cassandra. Use case, users. So this is the day and the age of millions of users, or same users producing millions of clicks. You're trying to funnel your user, see how he fits in, see what he did before he did the shopping cart, see what he did, where did he go, what did he tweet, and trying to connect the dots around your user. And that's one common use case we see where people, when they move to Cassandra, they're looking at trying to funnel and shape their users. Netflix, common example. Big marquee example for us. They are in production, and all the movies you're watching are all your user data for Netflix is on Cassandra running real time. So a couple of concepts are introduced here. Key, you need key. So most of these NoSQL stores have originated from key value stores. So being able to build a good key is actually a big answer to your problems. You're representing your data. Your data is also a part of your key. So your key by customer, it's a very read-heavy. All your plays as you play them on different devices are being stored in a column as they go, and it's a growing long row of columns. Cassandra can support up to 2 billion columns, but if you're not using lots of columns, then you're probably not using Cassandra's strength. At the same time, you don't want a big fat row, so that's other option, other thing to look at. Key by customer movie, so you want to know how a particular customer, if a bunch of customers are stopping a movie at a particular spot, we want to know if that's probably a problem in that video file. So again, you want to see how customers are watching. So that's the other, it's a write-heavy operation. You're writing all the And so that's the other high-speed writes is another common strength that Cassandra brings to the table, and so that's another write-heavy operation. Another common use case, time series. We see a lot of customers trying to build, trying to get data around their devices, or they want to get periodic readings, or even on their own applications. They want to know production application, how they are doing, how they are, what the performance is of the different stacks. Twitter is a common example. The Rainbird is a based out of Cassandra, trying to collect statistics on different pieces. Uyala, another common use case, doing time series style data. We see a lot of young startups who are not even up there, the big names who are using CloudKick was one of the earliest use case for time series as well. Metrics turns out, gathering metrics around data you've already collected turns out to be a much larger data set than actual data. So basically, you're trying to get the top 10. You want to shape your users based on different time series, the footprints they have left. All the data surrounding your core data is actually the stats tables end up being fast and furious. And so that's where you want to attack the problem with something that scales horizontally, scales without worrying about filling up your disk, or without worrying about how do you partition it. So partitioning comes in, naturally to time series stuff. So that's another common use case that people have when they're trying to shape their end user experience. So these are kind of common push towards going to NoSQL, and some of these users have chosen Cassandra, and here's a quick compendium of why. So the why Cassandra. It's operationally simple. Dynamo, Cassandra inherits a lot of its distribution model from Dynamo, Amazon's large-scale store, and has a schema from Bigtable. But for the most part, the distribution model, every node, it's peer-to-peer. So peer-to-peer has historically proven to be more resilient to scale. If you look at DNS, it's a very peer-to-peer storage of IP information, and it's scaled. It's scaled for the last many decades. So and so peer-to-peer, having no central point of anything, makes Cassandra very resilient to a lot of stuff. So that's and there's a quote one of our customer made, which basically, when an ops guy picks which NoSQL store to use, he eventually gravitates towards Cassandra. And that's been the case for most of our customers. They spend less time on the operations of how to run a distributed data store. When you're spending more time sharding your MySQL store, that's when you've arrived into big data. That's when you're ready for Cassandra. A little structure. Cassandra actually Cassandra is actually in a ring-like structure. Each one of those actually represent a node. Every node has a commit log, which basically is where it's a classic database concept of basically sequential logs, append-only sequential logs. And so when you send a write, for example, 3 nodes, and depending on what consistency level you've applied to it, you have 3 nodes participating in that write, for example, right there. So basically, it goes finds the key, the coordinator node finds the nodes that are participating in that particular key and stores it at the same time, and fires off the other 2 asynchronously. Now, sequential writes are very fast, and what that leaves is a very simple write model that also does replication. So it's happening while you're doing the write. It's not postponed to do a replication after the fact, after you build the system up, after you have your data on it. All your data is being replicated in the write. It's not it's an amortized cost of replication. So you're getting a lot of distribution out of the box. So what does that mean? Why do I care? So back in the day, only the financial services guys would have high available multi-data center uptimes and have that kind of availability. Now everybody can get it. Anybody who's able to have 2 nodes in 2 different availability zones will get that kind of availability. Whether it's EC2 or on your own machines. You can do rack-aware within your own data center if you want. So all of that at a very inexpensive cost of a single write. So every write you replicate. Another example there, showing 2 different data centers, DC1, DC2. Now, EC2 has multi-region, so you can use that over EC2 as well. When you read, you don't necessarily have to cross the boundaries of the data centers. So important to know is that you can actually separate your write performance from your reads. So you can continue to answer your queries locally. So you get that performance, you don't pay for your performance on the reads. So anyone here deployed on EC2 and have hit the outage on April 21st? So most people are watching Netflix, and Netflix was running on AWS, right? So and Netflix was using the multi-data center, multi-region, multi-availability zones features of Cassandra. So other Cassandra customers have survived as well. So let's switch gears to fast durable writes. Writes. I mean, the reason I got excited about Cassandra was I ran the benchmark, the YCSP cloud benchmark, and you look at that and I was like, maybe the numbers are wrong, maybe the digits are off. So maybe the data is not in there, right? So coming from Coherence and Oracle and other structures from big stacks from the J2E world, I looked at this number and was like, this doesn't make sense. The writes are super fast. You have to run it to know it. And the data is in there, and it is, so the crux of that is the commit log that we saw earlier. It's append-only, fast seeks, so cheap, inexpensive disks can get you fast performance. And it's not, it's not SSDs that are getting that performance. In fact, even on the cloud, ephemeral disks, which is the local disks, will get you better performance than the more expensive ones. So in some sense, writes are the workhorse of Cassandra. You can basically write a lot of writes and maybe orders of magnitude better, so in many ways. So single-digit millisecond writes are common for our customers in production, and fast reads, and you're not paying the cost at read time. We'll also double-click on the reads part. Writes, so single-digit milliseconds, append-only. Reads. So the other interesting nuance around Cassandra, which attracts really a lot of talent, is basically that reads, you pay your repair cost while you're reading it. So when you're reading data, you're actually repairing the entire the distributed system. In some sense, so just like you replicated while you wrote, and you amortize the cost of replication when you wrote, the reads are basically playing the cost of the part of homekeeping by just basically going through the system and seeing if there's any off data, fixing the data. So you're paying the cost of repair while you're reading. Now it does look like you're paying the cost upfront, and is that a good thing? No, but it turns out the reads are fast. They're not super slow, but the repairs are actually going to keep your data in sync most of the time. So that's kind of your the second interesting nugget from Cassandra world is that amortized repair actually pays off in the long term. Your data gets to be in better shape, and your one node is not too far off from the others. So there are a bunch of caches, key and row caches, and kudos to the HBase team which implemented off-heap. We also have off-heap on Cassandra now, so you get the benefits of escaping from garbage collection, JVM problems. Off-heap, JNA-based off-heaps. Indexes, secondary indexes are in the new Cassandra world, and but for the most part, materialized way of looking at things. Don't expect joins. Joins are not there, so materialize your schema to fit your queries. So we'll go back to the slide 1 at some point. You're paying the cost of materializing your data up front, your schema up front. So Clients, the preferred clients these days are SQL. Thrift is the serialization, deserialization format within Cassandra, and that still happens to be things that people use, customers use. Picasa, I've seen a lot of Python and PHP in our customer base, a lot of roll your own types from Scala and Clojure, but Hector leads the pack in terms of the number of Java clients that we have. So in number of clients using Java clients is Hector. PLOPS is a simple get your hands dirty quickly, so you can go and roll your own quick Cassandra client. So, but that said, Chromium, Ruby, and Clojure, we have Scala. So use case number 3, Hadoop. Turns out we started implementing a lot of Cassandra. Customers started implementing a lot of Cassandra scale, and we would help them get quickly up to speed and see what's going on. Eventually, they'll tell us the whole story and so we want to improve performance of the reads, right? So that's a common question that would come up. And we look at it and say there's a Ruby client trying to talk data from Cassandra or talk into Cassandra. And we look further, this client is actually reading from a cloud of Hadoop. So, the Apache Hadoop. So we would see that Hadoop was actually siphoning a lot of the data from log files, running a bunch of things, and then they're storing those into Cassandra, and serving those that data from Cassandra, whether it's analytics or real web apps. So this turned out to be a pretty common case for our customers, and that led us to investing time and building what's called Brisk. Brisk is a truly peer-to-peer Hadoop, and we'll see where that gets. But Brisk is essentially Hive plus HDFS plus Cassandra. So that's the Cassandra's entrance into the Hadoop space, where we're trying to see how we can solve the problems from there. Name node has been a problem in HDFS for a little while, where you're unable to put a lot of so all the inodes. Anyone who has, and I'm expecting Todd to really go deeper into this slide and explain some more of the HDFS Hadoop internals. But anyone who has seen Hadoop distribution installed will see that they're limited by the size with which the name node would scale. So one of the things we saw that there's an opportunity to make this all peer-to-peer. And basically, Hadoop in Brisk, essentially, in Brisk, we basically took HDFS and laid out the core inode and blocks as just basic tables. And any table essentially scales peer-to-peer across all the nodes in Cassandra. So here you see a piece where with the elephants inside, those nodes are Brisk nodes. You can continue to run the rest of your cluster as a Cassandra cluster. So this is 3 months in the making, and now currently in adoption in several customers. So and it's a BI, it's a very good play in the BI space, and people trying to use together low latency and batch together are working with it. We'll double click on some of the use case there, but the column families essentially are Cassandra's or big tables way of talking about tables. So you'll hear about column families probably more as you read through the space. So it's and essentially we took inode and sblock and made them real tables, and that basically puts them on Cassandra and on peer-to-peer. So for low latency, and you have a Cassandra data center nodes. And for batch analytics, you use Brisk data center nodes. What does that do to me as an application provider? You're now putting in logs through Hadoop into a cluster. You don't know what cluster, it's a Hadoop cluster. Now that data essentially becomes available for you to be run as queries through Hive or through basic even other operations that you can make small tables that can now serve real-time data or low latency data, near real-time data, low latency data for the rest of the world. So This brings together a problem that our customers were working a lot to connect all the dots of different pieces of the NoSQL space. The NoSQL space is the tail end of a real big space here, which is the Hadoop space. The Hadoop space is basically all your machine-generated data. All your machine-generated data today, most of it is going to HDFS. That's your store. That's a true high-scale store that's happening. And now the tail end of that, where you have now munged all this data, created a small little table or a small set of tables that you want to put, are now sitting on Cassandra, and you're serving them off of Cassandra to the rest of the world. That's a typical use case that we see. Of course, there is this flip use case where you want to put petabytes of data in Cassandra. That happens too, but Hadoop itself is a market that has taken off and is something we are aware of and are paying attention to. All right, pause in the talk. FUD. Let's look at what flaws and FUD that's surrounding Cassandra space, and we'll also look at some real flaws as well. Right. Consistency. So people talk about consistency in CAP's theorem and CAP theorem, and actually the paper that Bruno put up, Nancy Lynch, she proved the paper eventually. She was also part of Leslie Lampode's, she reviewed Leslie Lampode's original paper on clocks, which is another interesting tidbit from back in the day. Anyways, consistency, you hear RWN algebra when you talk about CAP theorem. What is RW? And then R is number of reads. W is the number of writes, or number of copies of writes. You make sure that that have to agree on a particular value. N is the total number of replicas. So given that, let's look at how this works. So what the CAP theorem states is if your read consistency and write consistency is greater than the total number of copies inside your cluster, you have a consistent data. Now how does this really work? Let's look at Oracle 2-node failover replication scenario. How does a 2-node Oracle be consistent? It asks reads from one node, so it asks for any one of the nodes to agree, and it makes sure that the number of write, every time you write to one node, it makes sure it writes to the second node, the W equal to 2, right? And the total number of copies are always going to be 2. So if you made a third copy and only wrote twice, then that would be not R plus W greater than N, and so it would be inconsistent, right? So if you made a backup last night and did not write to that backup, that would be behind today's data. So the reason R plus WN, or the reason Oracle replication works, even the big oracles, is because the total number of nodes is 2, and you always made sure that R plus W is greater than N. So this is the simple logic behind eventual consistency. This is a simple logic that we are saying that that's not going to bite your data. Your data is not getting inconsistent. There is an inconsistency window for every complex system, and that's different. The eventual consistency model has worked. DNS is the most popular eventual consistency eventual consistent system, and has scaled for us for years. So what we like to think about this is more as tunable consistency. And tunable consistency it gives you flexibility, so you can program consistency for the first time. All along, we paid the cost of always consistent all the time for every little application. So for example, the geocode of this particular site, it's not going to change in an eon. So why do I have to make sure it's locked heavily around, or why do I have to make sure it's not going to change? It's an immutable data. So let me actually get something that's not consistent, or try to not pay the cost of consistency for it. So for the first time, we actually have an application paradigm that actually allows you to program it, of course. And yes, there is cost with that. So, and that's kind of the big pushback you get is it's expensive to program thinking about all these. But that's what some of our customers are actually gaining from by not saying that I don't need to lock these pieces, and these pieces are fine with having a consistency level of 1 or consistency level of quorum. For high consistency, so regardless, the Cassandra programming model actually makes available all the levels of consistency. Cassandra itself has changed a little bit in the last few, and we have added consistency level from 0 to all for both reads and mostly and also for writes. So you can actually enforce a very high level of consistency, and you're trading off high availability. So that's kind of the piece. So if you enforce, for example, I want to make all the nodes right all the time, then even if one node is down, then you're basically paying the cost of not being available. And so that's the trade-off, and literally that's the trade-off in the mind, and at least part of this talk hopefully will get that across. So if you want a very highly available system, you want to write lots of copies and make sure you read from any one of them and you're fine, or any two of them, agree on the data and you're fine. So you get a pretty high availability through that. So that's the last piece there. And there is a ton of FUD, especially because RWN and N is usually confused with total number of nodes, which is different. You can have 100 nodes and you can just have a number of replicas be 2. So that's the other nuance. And the way it's been introduced in the original Dynamo paper definitely put a lot of discussion in this topic. So another common question that I get asked is, why is Facebook not using Cassandra anymore? And I just typed Facebook and Cassandra and Quora, and you see like a dozen questions which are all pretty much saying the same thing: which application is using and which is not. And I actually spoke to the team that wrote Cassandra at Facebook recently, and happened to connect with them and ask why. And turns out they actually only recently removed the application on Cassandra like a couple of months ago on inbox search. So inbox search was the original application that was actually running it, and it did scale for them. So the crux of that is it did scale for Facebook from 100 million to 500 million users. And that's a true story, and that's not made up. And if you are running into that scale problems, or if your context may not be the context of Facebook, essentially. And so it did scale for them, and it did use, and they were using, and we were all using it as part of that. So, and the average NoSQL deployment size is not nearly in that size, right? So it's a very small. The one we see is actually 12 nodes usually. So it's not the problem that you guys are going to face going out. Not all of us, anyways. That also gives a hint into another use case, which is search. Cassandra is actually used in conjunction with Solr as Solandra, which is actually an interesting product that we baked in the labs. Jake, whose GitHub account is there, essentially able to do Solr store on Cassandra. So essentially you can store on Cassandra and scale to petabyte scale indexes. So you can get the same kind of search interface that you got in Solr and Lucene, and use that on essentially using Cassandra. So that's another common use case that we do see. Eventual consistency is harder to program, and that's true actually, but it's also a flexibility you have. We never had it. We always were paying ACID. C was always taken from us, whether it was MySQL or Oracle, we always were paying for that. But as you put yourself in a person who's sharding MySQL for the first time, you understand that you're inventing eventual consistency while you're doing that. Some of our customers who chose Cassandra, they're filling up the shard faster than they could shard. But the crux of the argument that I make is that the average customer has mostly immutable data. If you're using Hadoop, you've written the log file last night, right? The data is already immutable. It's not changing. So you're mostly immutable data, and complex systems at scale are only halfway consistent anyway. So if you had a big GC pause on one of the node, that node was behind on data, and that was true for WebLogic, right? So it was true for the previous stack as well. Other miscellaneous myths that are around Cassandra is like you probably have partial rows, or you have data loss. No, we have a commit log. It's per row, and it's actually and it's very it's a sequential append only. If you lost the disk, we still recover from that with the commit log. So we actually have a test, and some of our customers also have tests where they kill the disk and make sure everything is fine. I actually was at a customer who, over the turn of the Christmas, had a big customer jump onto their analytics cluster, which was not very large, but one of the cluster was filled up and they didn't know what to do. And I said, just don't worry. And it really, we migrated everything into a bigger, larger disk system and then doubled their setup, but it really did not inhibit them from running their app. So that node was out of action, five out of 6 nodes, 1 out of 6 nodes, and the rest 5 nodes performed. And essentially, that's what you're paying for. Really, when you are in the thick of it, and when you need to scale, that's when Cassandra. That's when you would thank Cassandra, actually. 3 more reasons for using Cassandra before I run out of time. One is tools. A bunch of AMIs have come out. DataStax AMI is the one preferred. Ops Center is a DataStax tool again, which allows you to look at data, look at your app, look at your cluster, and be able to perform operations on it. It's kind of a JConsole with a very clean JMX presentation. But JMX is, every little nuance around Cassandra has been JMX'd, so you can actually look at all these metrics. Cassandra is one of the most, I've worked on JBoss when it was pre 1.0, so looking at, when I saw that JMX richness of JBoss, I was like, wow. And Cassandra made me wow again, because it definitely tracks everything through JMX. It's a very well nuanced project around metrics. App Dynamics has a pretty cool tool around Cassandra and other apps as well, so definitely check that out. Another big reason that attracts Cassandra is its beautiful code. It's new code, and it's actually a lot smaller than you think. When I started looking at it, it was about 75,000 lines, and the last 1.8 version, we close to 90K as of last night. And it is Java, so most people who are here from the Java land will automatically be able to look at it, look and pour at every piece of it. It uses mostly concurrent collections, so skip plus, you'll see at the core of the architecture, you see very interesting, good collections. So if you're avid reader of code, you love Cassandra. It uses annotations, Bloom filters, Merkle trees, lots of interesting, good data structures. These are real hard problems, guys. Distributed counters, very hard problem, right? So people have done that before, but you get to invent them again, see them again, and it's happening. It's not like the product is getting to be 1.0 soon, right? So it's non-blocking. It uses non-blocking I/O. It's staged, so when you actually do a node tool stats, you will actually see the stages of where each of these stats are, where each of these thread queues are. So it's a staged architecture, so you can actually see a lot of interesting nuances there. The current focus around counters and CQL, which is trying to make it less, trying to make it easy for people to get in. That's one of the hardest, biggest critique of Cassandra, and somewhat valid for so far, is it's very hard to get into using it from an end application standpoint. And a lot more gaps exist there and are being fixed, and we're trying to make a simple client so you can actually use it. And so the flip side is true for Mongo, where the client is dead simple to use. You can actually use it right away. So so credit where credit is due. Cassandra is actually is now focusing on making that dead simple for end users. And there's a lot of operational smoothing that's happening, hardening before 1.0, and more of that will as we go forward. The community behind Cassandra, as I mentioned, that's kind of the biggest reason to choose and learn Cassandra and use that as your NoSQL place. It's a very robust, it's rapid. Hash Cassandra is active 24/7. I have not seen it be empty any time of the day. Most people, even the Jonathan Ellis, who's the founder of DataStax, is one email away, and usually his email arrives much faster than my own boss' email. So, these are really very passionate engineers, young set of engineers behind this project, DataStax, as well as the people who did work on it. And there's a bunch of engineers, both independent consultants, startups, Reddit, other startups from San Francisco, rest of the world, large companies, Rackspace, Twitter, Netflix, all of them are behind this. It's not a project that's going away. So come join the efforts, and that's kind of one thing that I would say. Before I leave, here's other trends that we see, job trends. Downloads don't speak well, so job trends of Cassandra is on the up. And use case, numbers are off. Another use case is first NoSQL, then scale. So when your first NoSQL may not be the one that you're going to be using for scaling. So the move from, Netflix actually characterized their move from RDBMS to NoSQL was 1 long year. And then once they got there, moving to Cassandra was a week. But getting to NoSQL is actually a very harder developer journey because you have to think queries first. You have to think queries and how the data is growing and all. So all that journey, we have to give up a lot of the goodnesses of RDBMSs and move to NoSQL. That's a bigger journey. And so the common use case we see is people go to SimpleDB, which is easy, and then move to Cassandra. Netflix is an example there. People go to MongoDB, and I just converted a MongoDB customer over the weekend, and then to Cassandra. So it's a common, it's easy to get in there, and then when you really need to scale and you're pulling all the operational pieces together by yourself, when you're rolling them on, that's when you're moving to Cassandra. So job trend 2 is Cassandra and Mongo, and job trend 3 is Cassandra, Mongo, and HBase. So HBase is definitely on the rise, and it's also, so is Cassandra. So it's good. So that's, and actually there's a job trend 4, which I did not put, but it's the sum total of NoSQL is these 3 guys, and they're playing very well. And that's it's a healthy requirement for the space, and we need that. There is a 4th one that was coming up. That's for the uncle. We want a standard, right? So we want to standardize all these, and then we create a newer version of QL. So it's not necessarily it'll work. But there is different flavors of NoSQL, and you'll hear the rest of them. And there is a healthy learning that's happening within the system. We learned a lot from HBase, and HBase is picking pieces from Cassandra, and so is Mongo. So all these things are not static. They're changing as we speak. If you Google up any of these, some of those blogs of 06 are no longer valid for 08 version of Cassandra. And some of the pieces of HBase or name nodes will not be true in the future. So things are changing as we speak, and these slides are dated, and so are current but dated. So I see a future where all of these guys will be robust enough to become your database of choice. So in summary, Cassandra is a high-scale peer-to-peer distributed database. Questions? The question is Apache Couch. Are you asking for difference between Apache Cassandra and Apache CouchDB in terms of how Apache treats them, or?
Yes.
I'm not the Apache spokesperson for this, but I've seen really fairness on their part so far. I don't see a reason one should be preferenced or the other. I mean, they're just, in Apache's ways, there's mostly peers. There's no reason to be worried about losing or gaining from an Apache standpoint. Historically, Apache played community over code, and they stuck to that. And so if there's a community around CouchDB, it's going to be there for a long time. So I don't think that's probably not the reason to go either way. But the main reason is what you said. One is very distributed and peer-to-peer. Another one gets you up and ready with NoSQL, and that's good. So both play their roles. Yeah, very well. Yeah, so I think that's more of a good panel-like question. Be great to have the other speakers finish, and we could get back to the same question, if that makes sense. The question is, how do these different players work? And I think Cassandra definitely, clearly is designed to make sure your data gets durably written and written across lots of nodes, so you don't need to worry about availability. And it's partitioned, and so it's clearly focused on making availability and partitioning the key focus. So if you're a small website, you don't have to be a Netflix or a big large company to be using Cassandra. If you're a small, and we have a lot of small startups actually using it. If you're on EC2 and you want to, and today, yes, even today there was a EC2 outage. So if you're worried about uptime on your EC2 setup, you should be thinking about Cassandra. So it's When you can't fit things in memory on one box, so if you, when big data, the definition of big data is if it's not fitting in today's memory, all in memory, and you can fit all the users' data. It's a billion rows. 6 billion rows can actually fit in memory on one box these days. But once you start mining that data and creating data around it, that's when data falls off one node. So if you're doing multi-node data stores, you can't pay the big bang for exadatas and the big systems, then your choice is having to partition it, having to run on multi-node nodes. And that's the context behind all NoSQL, essentially. So the question is, at what point do I move from Mongo onto Cassandra? Right? It's a much longer, nuanced question. Apologize for chopping it, but the question. So Mongo is dead simple to program, and it's. I mean, even I love that. It's an interface that you just basically. It's very simple. Speaks like Java. You write it, and it's there, right? It's a JSON style table, so everything is JSON, so you understand that as a JavaScript developer, you can see that, see how your app looks like. So it's a very good programming model for end users. What happens is when it actually falls to a larger than one node setup, when you start putting many nodes on it, when your data scales. Remember the whole reason we were coming to NoSQL, throwing away all the goodies that Oracle built for us or IBM built for us, or all the big databases, right? That's a database theory for 10, 20 years. We threw all of that off, as well as the caching vendors, because we want scale, right? So the only reason to come to NoSQL, or the prime reason to come to NoSQL, is scale. And when it scales, so the whole replication, the whole read and repair, and being able to get a large system to agree on a few queries, that whole nuance of maintaining it, that's when people move from using a traditional MySQL or a Mongo into Cassandra. So the use cases we see today are data that suddenly your app becomes more popular than you expect, and then you see higher number of users, higher number of reads, higher number of writes. And so write speeds obviously speak very well for Cassandra. And so that's, I mean, language is not the reason people are moving to Cassandra. The main reason they're moving from Mongo is really because of scale and being able to kill your app mercilessly. I mean, I actually tell my customers if they are worried about restarting their Cassandra, I said just kill it. It's designed to replay everything that's in memory or not flushed. The commit logs, every time it comes up, it actually replays everything. So I mean, we actually believe that the apps that live long enough are designed so they're fault tolerant that way. So fault tolerance, and when you're getting to the data sets that are not fitting on small number of nodes, and replication, when you do multi-data center replication, and all these features are coming into those databases. So I will let those authors speak for them. Actually, those are the features that they are also seeing customers, and the market wants the same thing. They have the same problems. They want the availability. They want some level of consistency. They want partitioning, right? So the market wants all of them actually, and they want them all to be easy to use. So that's what the average designer wants, and so all these NoSQL stores are slowly heading towards that. So anyways, I hope I answered. So there are some numbers around it too, but really when you try to get beyond a few nodes, you quickly find yourself at the mercy of Mongo's scale. So the question is, how does Cassandra handle backups? So it's not something we don't worry about. Our customers have incremental, and so there's a global snapshot. So you can take a global snapshot, and you can take node snapshots, and store these. The files are actually, so you have commit logs and data logs. So they're usually run on different LUNs as well, so they get good performance. But so you take snapshots and then you take incremental backups. Our customers take copies of these files and put them on S3, for example, and then take incremental deltas on them on their local. So it's a regular file system backup. The actual app does not have any state. So all the state is in the YAML files or the database and log files. So it's all file based. So, and we don't do anything fancy on the file itself. It's real raw data, so hex data. So there's nothing that stops you from taking that snapshot and creating a new cluster. So yeah. And one of the features for the Op Center is to actually press a button, do the same thing, get a snapshot. Essentially, there's a set of things that you do before you take that snapshot, which is basically flush and repair and compact, and then take a copy. So it's not a, people do that all the time, yes. Thank you for being here.